So there's one last thing in section 2.1 we need to take a look at, and this is the idea of how to estimate derivatives numerically from a table of values. We've got a table of values over here, really only know 4 points on that function f of x, and somehow I want to try to approximate the derivative at x equals 9, 11.5, 15. Here's the idea. This graph may not necessarily represent these values, but it'll work for what we're trying to do. Let's say I have some function with these 3 points over here, and I want to approximate the derivative over there, the slope of a tangent line at that point. I have no clue what exactly is going on between those points on the function. I'm just going to take an educated guess and say, I don't know, maybe the function looks like that. We have no way of knowing this. The function could be all wiggly and wave, whatever. But the deal is, if I want to estimate the slope over here, a pretty good approximation is just the slope of the secant line through those 2 points that are around the point where I want to find the derivative. I think that secant line has a pretty similar slope to that tangent line. Do I want to write this in the notes? Yeah, I think we should probably write this in the notes. One line we're going to write in our notes about numerical derivatives, and then we'll go to that worksheet. Numerical derivatives. To estimate derivatives from a table of values, we're going to just find the slope of the secant line through 2 points around the x value we're trying to find the derivative at. To estimate derivatives from a table of values, find the slope of the secant line through 2 points around your x value. To estimate derivatives from a table of values, we're going to find the slope of the secant line, the line through 2 points, well, around your x value. Actually, I shouldn't have said points, I should have said 2 points. To estimate derivatives from a table of values, find the slope of the secant line through 2 points around your x value. Let's do this. This is not going to be super hard, but this is actually a big deal on the AP exam, and I can pretty much guarantee you're going to have to do this as part of a free response question. F prime of 9. Well, 9 is in between 8 and 10, so let me just find the slope of the secant line through x equals 8 and x equals 10. This is completely an approximation. I could be wildly off, but this is the best I can do from the very little information I'm given in that table. I'm going to say f of 10 minus f of 8 over 10 minus 8. So my approximation is 23 minus 20 over 10 minus 8. That's 3 over 2. That's all we're doing. You go try letter B. F of, let's see, 11.5 is in between 10 and 13. So f of 13 minus f of 10 over 13 minus 10. 26 minus 23. Oh, this is actually going to be nice. Over 13 minus 10, you're going to get 3 over 3. You're getting 1. Go do letter C. This is f of 17 minus f of 13 over 17 minus 13. That is 30 minus 26 over 17. Oh, actually, I think this is the same value we got for the other one. Maybe I should give a different table of values next year, but I think we should be getting 1 for that one as well. Last one, which was basically taken off an AP exam, modified from an AP exam. As pot of tea cools, the temperature of the tea is modeled by a differentiable, which also means continuous, function h, between 0 and 10, where T is measured in minutes and the temperature H is in degrees Celsius. Values of the temperature of the T are given over here. In letter A, I want to approximate the rate at which the temperature of the T is changing at time T equals 3.5 and show the computations. Okay, well, this means I really want to approximate H prime of 3.5. This is the same deal we did before. Take a moment and go find the value of H prime of 3.5. My approximation is H of 5 minus H of 2 over 5 minus 2. 52 minus 60 over 3, negative 8/3. It's okay that the derivative is negative. That means the T is cooling, that it should be cooling. I need units here. Any thoughts on what the units are going to be? This should be similar to what we did on the first day of this unit. The top is a temperature minus a temperature, that's degrees Celsius minus degrees Celsius, so degrees Celsius, over, the bottom is minutes minus minutes, degrees Celsius per minute. Go do letter B. Okay, so H prime of 7 is going to be about H of 9 minus H of 5 over 9 minus 5. That is 44 minus 52 over 9 minus 5 is 4. I think that's negative 8 over 4 if I'm subtracting correctly, so negative 2 degrees Celsius per minute, which means it looks like it's cooling a little bit faster at time 3.5 than time 7, which should make sense. When you first take the T out, it's going to be really hot and cooling down quickly, and then as time goes on, it's still cooling, but it's cooling slower and slower and slower. And this does it for section 2.1. You're going to like section 2.2 because we're suddenly going to learn a lot of shortcuts for calculating derivatives.